Good morning and welcome to our continued discussion on analyzing functions and graphing. Like always, can I just get confirmation in the chat that you can see and hear me? Then we can get going. All right, sounds good. Now, yesterday we ended with the beginning of step 2. I'll remind you what the steps are. Here we are breaking it up into 5 steps because I have 5 fingers and I can remember 5 things, not too overwhelming. And we discussed the first one where I'm just gonna look at the function and see if I identify it as a specific type, if I know something automatically because of that type, and I can find a y-intercept to make myself feel as if I've made progress. The second step is really the first big one, where I'm asking, are there any asymptotes? What's the long-term behavior? Trying to get more information about the graphs in these extreme situations. And then we have some other steps that we have to get to when we get to it. We are also going to mainly focus on 5 types of functions in increasing difficulty for the most part. We'll start with polynomials and work through them. So for step 2, I want to look at an example for each of these at the very least. This one. Okay. So we're going to have the same examples we had last time and just do a step for each of them as we go. So I wrote them down again just so we have more space to work. In the asymptotic behavior category of our analysis, we are asking a couple of things. We are asking, are there any vertical asymptotes? Now, we're going to keep things fairly simple, and the vertical asymptotes are mainly going to be, roughly speaking, where the function is undefined. Now, in the case of a rational function, that is going to happen when the denominator equals 0. So, for the most part, I'm mainly looking for situations where I have a fraction and I'm dividing by 0, where the top is not 0 technically. So in this case, to better see that, I want to factor. So I'm going to take an x out for the top and be left with x minus 2. Then I'm going to factor the bottom, and we have done this, but it's good to just see it again. X and x, a minus 3, and a plus 2. Technically speaking, the vertical asymptote is going to be at some x equal to c when the limit as x approaches c of my function is plus or minus infinity, technically. And for the rational function, as long as I don't have the same factor at the top as well, it's when these bottom guys are going to equal 0. So there's no need, if I understand what I'm looking for, there's no need to set up a whole limit and do a whole thing because a rational function is a fairly straightforward function. But technically speaking, I have to make sure the y value actually blows up in size. And because I've identified it as a rational function, I know that's going to happen as long as when I see an x minus 3 at the bottom, there isn't an x minus 3 at the top as well, because then the limit is going to exist probably. And the same for the other factor I see in the bottom. That is the case, so I'm good to just state the vertical asymptotes. So vertical, excuse me, vertical asymptotes are, of course, horizontal straight lines. Not horizontal, vertical. It's in the word, vertical asymptotes. And that's going to be at x equal to 3 and x equal to negative 2. Now you might ask, well, if I set this up, and I know we're repeating ourselves a little bit, we have a vertical asymptote here at negative 2. We have a vertical asymptote here at 3. As I approach these lines, I know without much effort, because of the rational function I've identified, that is going to behave in one of these two ways, but I don't really know which one. And with the x squareds, I don't know without a little bit of effort. If you want to know which of these arrows it will be in each case, there is something we can do, and it's worth seeing at this stage. So what I want to do, actually, I want to see my function. So I'm just going to backtrack on the graphing here. Can I go far enough? Can I go far enough? Yes, I can. Far enough. Okay. I want to set up a number line, and it's going to be the x-axis, really. And I'm going to mark all numbers where the function equals 0, which means any one of these factors can equal 0. In increasing order, I have a -2 for that bracket. I'm going to have a 0 for the x. Any one of these, not just a function, any one of the pieces, the factors equaling 0. I'm going to have a 2, and I'm going to have a 3. And I'm going to split my x values up according to those numbers. Then I'm going to list all the factors that I see in any order. It really doesn't matter. X minus 3, as long as you have everything. Now, by way of multiplication or division, they are going to give me the function values, the y values. Okay. Now what I'm going to do is just look at each of these pieces individually. Well, x is 0, right in line with 0, of course. And it's going to be negative to the left, positive to the right. So what I've done by marking off these 4 values, I've split my x values into 5 intervals. In each of the intervals, this piece, which is a very simple x, is of course going to be positive or negative depending on the value. Maybe the next one's a little more interesting. The next one is x minus 2. It's going to be 0 when x is right on this line at 2. Anywhere else, it's either positive or negative. So when I have a number, maybe in this compartment over here, this interval, it's less than -2. If I plug that in, like a -3, for example, I get -3 minus -2, which is -5. So I get an answer that is negative. And that's going to be the same for all of these in this interval. In this interval, for x values between -2 and 0, I'm subtracting 2 from them. It's going to be negative. If I have a number less than 2, actually, the answer to x minus 2 is always going to be negative. But if I have a number greater than 2 and I subtract 2, I'm left with a little positive bit. It doesn't matter how much. The only thing that matters right now is if it's positive or negative. And I go down the line and I do that for all of these. X minus 3 is going to be 0 when x is 3. Anything less than 0, anything less than 3 for x, if I subtract 3, it's going to be negative. Anything more than 3, which is only this right interval, I subtract 3, I still have a little left. Then the last one, and all of these are very similar. They're all linear factors. X plus 2 is 0 when x is -2. Anything less, it's going to be a negative. Anything more, it's going to be a positive. But please make sure you understand for each of these sections why it's a plus and why it's a minus. You need to have the confidence to fill in the pluses and the minuses. Later on, these factors might look different, and it's not just, oh, it's always minus and then always plus. No, it depends on what they are. Okay, so now I've filled this in. Please stop me if you're not sure. Why have I done this? Well, remember I've broken my x values into these 5 intervals. Let's look at the first one. When I'm in this interval, the y value is calculated by multiplying these numbers or dividing these numbers. And because I have 4 negative numbers, regardless of what they are, my answer is always going to be positive. Always. 4 negatives in multiplication and division will make a positive answer. I don't care how much it is. I know it's positive. When I'm at x equal to -2, then this x plus 2 bracket is going to be 0. And it's going to cause the function to be undefined. I just indicate that with a cross there. Bad times. There is no y value. It's undefined, right? I can't divide by 0. Next interval, it's over here, between -2 and 0 for x. It doesn't matter what the y values are. What matters is I'm going to have 3 negatives and a positive. Multiply or divided, the answer will always be negative. Then at x equal to 0, the factor that is going to equal 0 is going to be this x. It's in the numerator. Plug in 0 if you want. It's going to make a y value of 0. There's a difference between a factor when it equals 0 being in the numerator and in the denominator, and people struggle with this. If there's a 0 in the numerator and nowhere else, the answer is 0. If there's a 0 in the denominator and nowhere else, the answer is undefined. Okay? There's a difference in where these factors appear in my fraction. Then between 0 and 2 for x, next interval, I have 2 negatives, 2 positives. The answer will always be positive. I don't know how much it is. I don't care. At x equal to 2, the x minus 2 bracket is 0. It's in the numerator. It makes the whole thing 0. For the interval 2 to 3, I have 1 negative. My answer will be negative. At x equal to 3, this bottom bracket is 0, making the whole thing undefined. And for the interval 3 and up, all positive numbers will create a positive answer. Now, how does this help me? It is going to tell me exactly what is happening as I get close to these asymptotes at -2 and 3. Because if I get close on the left towards x equal to -2, I'm just to the left of -2 on my number line in my table. For those, anything to the left have positive y values. I know it's going to be either going up or going down. The going down ones have negative y values. So it can't be going down. It has to be going up to fit with my table having positive y values. Just to the right of -2, I have all negative values. So it has to be that arrow. I know it's one of the two because I've identified it as a vertical asymptote. Otherwise, this wouldn't work. So I know it's going to be either going up or down. Which one is it? Well, this table tells me exactly. Where's my next asymptote? At 3. Just to the left of 3, I am negative in my y value, so the arrow has to go down. Just to the right of 3, I'm positive, so the arrow has to go up. So in this way, by analyzing the positive and where each factor is positive and negative and how that contributes to the function, to the y value being positive or negative, I can pick which arrow is which. I also get the y-intercepts for free here at 0 and at 2. But what the graph looks like past this, I don't know. And that's also not the question. So it's, for me, very handy to see this table. And it is a way if I want to pick which arrow is which in step 2. All right. A lot of things are going to happen perhaps really fast. So whenever you find something and you're not sure, I'm not wasting your time. If I'm doing this table, it's because it is extremely useful. And if you need to put in some time and master it, you are not wasting your time. Next up is the horizontal asymptote question. So step 2 has two parts to it: vertical asymptotes, horizontal asymptotes. Horizontal asymptote question is where I'm looking for the actual limit. So I want to set up a limit, and I want to do it in the classic way I've seen before. So now I have to remember my questions here. Limit x goes to infinity. I think it was x minus 2 over x. Sorry, my memory is terrible, but that's okay. In this case, I actually don't want to see the factors. I want to see the polynomials in the numerator and the denominator. Why? Because I know that for this infinite limit of a rational function, the answer is the ratio of the leading terms, and it's 1. Don't look at the factored version, look at the simplified version. And the limit as x approaches negative infinity of the same function, writing it out again. I'm doing exactly the same thing. It's also 1. So, bonus to identifying it as a rational function is if I find a horizontal asymptote, and I do, y equals 1. Let's put it up here. Boom, 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 boom. It's always going to be the same on both sides. Same on both sides. It's always the same. However, I don't really know how the graph is approaching this line. I don't really know because my table doesn't tell me that. All my table says is past 3, the y value is positive. Well, yes, but it doesn't tell me is it greater than 1 or less than 1. So there are limitations to doing this table this early in that I can answer some vertical asymptote arrows, but I can't really answer everything. Not saying it's impossible. I'm saying with a lot of extra effort, maybe I can find the arrows. I don't really care. I just want to find the asymptotes. Because it turns out when I do step 3, choosing the arrows are going to be quite straightforward to do. And I don't need to put in extra effort here. The only question here is to get a rough image of what the graph is doing. I might want to do vertical asymptote arrows, but just find the asymptotes. Don't worry too much about exactly how it's approaching those asymptotes at this stage, because this is only some pieces of the puzzle. It's not all the pieces. When I have all the pieces, everything will fall into place. Don't worry. People get a little flustered because they want to know everything when they do a single step or a single portion of a step. No, just do that. Only when we have all the information can we really do everything. Right now, can't really. So here, in my next example, it's a polynomial, and that means I have no vertical asymptotes. Half of step 2 is done. Easy. And for horizontal asymptotes, well, I'm answering the limit question, right? It's going to be, I'll copy my function down here really quickly. But I see it's a polynomial. It's whatever the leading term does. It's infinity. Does not exist. No vertical asymptotes. Actually, it's a plus or minus there. Actually, yeah, that's not true in general. In this case, because it's x to the 4, I get both answers. But regardless, it does not exist. There will be no asymptotes for a polynomial. So step 2 is trivial. There's virtually nothing to do. However, I can say a little bit in terms of the long-term behavior, as little as I can say, which is extra information, and I do want to include it if I'm ultimately looking to graph it. Remember we had a y-intercept of, was it 7? So what do I know here? I know that long term, when x goes to positive infinity, I'm going to go up. I don't exactly know how, but I know I'm heading that way. Long term, when x goes far to the left, I'm going to go up. I don't know if my arrow is positioned very well, but its direction is. That's all I know. What happens in the middle here? No idea. But that's not what step 2 is trying to answer either. So there is some information that step 2 can give me, even if there are no asymptotes. Just get rid of that like that. And I do want to include that, and I do want to be aware of that. So the limit not existing is not sufficient. I want to know, does it go to an infinity? Which infinity? Put that in your graph. Get more information. It's pieces of the puzzle. Okay. So I don't want to spend too much time on rational functions and polynomials because these things we've done before. These other types of functions have something new that we need to focus on. And there is a lot to do. So perhaps you feel I'm going a little fast at points. Feel free to stop me right now. Or if you feel like that, just rewatch the video many, many times. That's okay. It's all good stuff here. All things we need to be able to do. Nothing here is wasting your time. Okay, so for this exponential component type of function, I saw that I don't love the look of negative exponents sometimes. I want to also have the option of seeing it as a fraction when that's appropriate. And when I'm answering the vertical asymptote question, that's very appropriate because this vertical asymptote is only going to happen when the denominator equals 0. However, in this case, it's not a polynomial anymore, right? So I can't factor e to the x. But I know what e to the x looks like. I've memorized it. It's a basic function. There it is. I should know it perfectly. All its properties. Asymptote on the left, infinity on the right, blah, blah, blah. So this guy is always above the x-axis. It's never going to give me a y value of 0. So that's never going to happen. And so I have no vertical asymptotes because of what is in the denominator. All right. Everyone good so far? A lot of things are happening. I don't know how you feel. In the past, people do not take the time to memorize the basic e to the x function. And then when they get to little things like that, they think there is an x value that makes it 0. I literally read it off my basic function. It never crosses the x-axis. And that's where the y value is 0, right? Which means the y value can never be 0. It's so simple. I read it off. There is nothing to think about here. All right. Feel free to interrupt me. You came all this way for a live session. Use the opportunity if you're not sure. The horizontal asymptote question is a different ballgame for this kind of function. Now I'll set it up because that's what I have to do. And I have to do the negative one as well, but one thing at a time. So this is the question, right? This is the question. Do we learn transformations of this function? Which function? E to the x? Yes, we did that. Yes, it's a basic function. It's in my library, just like the natural log function. Now, I did one example for sure. We did it on 2 to the x, I think, or 3 to the x, but they all have the same shape. E is just actually between 2 and 3. There are many exponential functions by just changing the base, right? And I can do transformations on all of them. So technically I have a ton of basic functions, but they all pretty much look the same. Whether it's 2 to the x, 3 to the x, e to the x, it's all the same in terms of shape and properties. All right. And ever if you transform it, y will never equal to 0. No, of course, if I transform it, y will equal 0. I could shift this down and then I have a y value. But look at this. I've isolated the denominator and I'm asking if that is equal to 0. What is in my equation is not a transformation. It is the basic. And because it's the basic one, there is no 0 for y, ever. If it was a transformed one on the left here, well, it's a completely different game. But it's not. It's the basic one. And most often it will be the basic one. Okay. No problem. Please ask. It is not a problem. Okay, so now the horizontal asymptote question. Realize that it is a completely different question. It is not the same question. Just because they're both in step 2 does not mean I do the same thing. I do nothing the same. This one is asking for a long-term behavior when x goes to infinity, of course negative infinity as well, one thing at a time. What is the form of this limit? What do I mean by that? We're building on those things. We can't forget any of those things. The numerator goes to infinity. The denominator, just e to the x. Read it off. It goes to infinity. This is an indeterminate form. Indeterminate form. Just like 0 over 0, we have mentioned it. You can go look at those videos. I know exactly what we said. When I have 0 over 0 or infinity over infinity, it is a pickle. We focused a lot more on 0 over 0, but we did see it for rational functions as well, that when I have infinity over infinity, really anything can happen. I don't know. I cannot determine just from looking at it what the answer is going to be. Okay, so here I have the same issue. In the rational function, which was over here, I had that issue, but because it was a rational function, I already knew how to handle it. And we did our factoring of the highest power of x to prove that it's just the ratio of leading terms. So I can get around the indeterminate form because the rational function is more familiar. It had a technique that told me that I could just look at the ratio of leading terms and I could find the answer that way. In this case, it's not a rational function anymore. You're still on the vertical asymptote, aren't you? There is no solution. In order for me to have a point that has a y coordinate of 0, I have to sit on the x-axis. Oh, sorry. I don't know. You didn't specify. Uh, there is. I'm asking for a long-term question. The fact that I have a y-intercept of 0 doesn't mean that doesn't say what's happening long-term. And sometimes these pieces are going to change, right? It's not always going to be an x. It's not always going to be an e to the x. So I'm not saying this one is the hardest one ever, and some of you might have a good intuition and say that it's 0. You're not wrong. But when things change, when things get more complicated, what do I do then? And when my intuition fails, I want to come up with a method to handle it, whether it's easy or not. Okay, it's not obvious what the answer is. We've never seen this before. So I can't just assume, why don't you see it? It's 0. Why not? No, I don't know what it is. I've never seen this before. What do I do? So that when it gets hard, I can rely on that. The most important thing here is that in general, when I have an infinity over infinity or 0 over 0, I cannot say that it's always going to be something. I don't know what it is. Luckily, we have a method to do it. It's a little advanced, I suppose, but it's essential for something like this. And it was developed long ago by a Frenchman, and it is therefore called after him, L'Hopital's rule. Now, I'll just write out what it says in general. In a limit, it doesn't matter what x goes to. It could be finite or infinite. I don't actually care. When I have a function, let's call it, yeah, it doesn't matter, f of x over g of x. Not a rational function necessarily, but it could be. If I have a limit like that, if it has the form 0 over 0 or infinity over infinity, then let's say it like this, the limit equals the same limit, x goes to the same thing, of the ratio of the derivatives. Now please don't read into this more than what I'm saying. It's not, well, to me at least, it's not obvious how this could possibly be, and the proof is unpleasant. I can't really do it here. It only says if I have an indeterminate form, it turns out that the ratio of numerator to denominator approaches the same thing as the ratio of the rates of change. Why? Who knows? I have no idea. It's not intuitive. But when you prove it, it's confirmed. And I have a ratio denominator numerator here. So I have a fraction situation. I've identified the form as one of the indeterminate forms, so L'Hopital's rule can be used. It can only be used in these situations. And only then can I say I'll write it out. The limit is going to be the same as the limit of the two derivatives in the same place as the original numerator and denominator. The derivative of the numerator, derivative of the denominator. This is not a quotient rule. This is nothing like that. It is completely different. Okay, but essential to be able to handle limits, especially with exponential and log functions. I don't have a rational function shortcut anymore. Derivative of the top is 1. Derivative of the bottom is e to the x. What is the form of this limit? 1 over infinity. And we've seen before, if the numerator is constant, the denominator blows up, the whole thing shrinks down to 0. Okay. So there's a lot more going on here, and it's because one of the pieces is not a polynomial anymore. L'Hopital's rule is very handy to tell me how this thing behaves, but I can only do it for a limit that looks like this. So I'll squeeze it in here. Let's do it like this. Horizontal asymptote is there. It is y equal to 0. Now, you were completely correct that it is y equal to 0, but it is not obvious why. Without a sense of these functions and how they relate to each other with some experience, maybe, but very easily I can have something and I don't know what it does anymore. I have to have a fallback method, and L'Hopital's rule is that method. So we had no vertical asymptotes. We have a horizontal asymptote when x goes to infinity. I also have to check when x goes to negative infinity. There are two sides for the long-term behavior, right? I've only done one. I only did infinity. So let's see. Actually, I want to leave L'Hopital's rule up here. Can I use L'Hopital's rule again? Can I just take the derivative of the top and the bottom? No. I can only do that if the form is 0 over 0 or infinity over infinity. It's very specific. If it doesn't work like that, I cannot do this. It is garbage. What is the form in this case? Well, it's an infinity I don't care which one. Positive, negative. It's an infinity for x, right? What about the bottom? I read it off my graph. It's a basic function. When x goes far to the left, e to the x goes to 0. This form is not one of the two types allowed in L'Hopital's rule. Therefore, I cannot use L'Hopital's rule. It is going to be something else. But think about it. It's not an indeterminate form. I can totally see what's happening here. Okay, it's negative infinity, fair enough. The numerator blows up in size, and at the same time, the denominator shrinks down. The whole thing is going to blow up and be negative because I have a negative number in x, positive number in e to the x. There is no issue. It's not an indeterminate form. L'Hopital's rule only helps me when I can't figure it out any other way. So there's no horizontal asymptote on the left. And there is a horizontal asymptote on the right. So what I see in contrast to the rational functions where the horizontal asymptote is always going to be the same on both sides. I don't have that symmetry anymore. For something with an exponential component, I could have a horizontal asymptote on one side, but not on the other. Let's have a picture of what we have so far. There's my setup. I had a y-intercept of 0, if you remember. Now I have a horizontal, I have no horizontal asymptote on the left. In fact, it's going down on the left. I have a horizontal asymptote on the right. It is the x-axis, essentially. I don't know how exactly this is going to happen, like that. Now I'll preview this for you because it helps perhaps to see how could this happen. But please know that you are not supposed to know what the graph looks like just after step 1. We don't have all the pieces, but I'll show you what it looks like so you can see how this could happen. I'm going to be a little curvy here. I'm going to do it just so I can draw it easily. Like this. Come on, buddy. Curve in there. Something like that. There's a top there. I have a horizontal asymptote on the right, not on the left, and I'm crossing at x equal to 0, y equal to 0 as well. So I get these kinds of more interesting graphs, not super complicated. Once I see all the pieces, again, this is not obvious right now. All I've identified are these things in the circles. Later on, I have to get more pieces to the puzzle and it'll fill in this shape. My drawing isn't very good. So it's a completely different story to find the horizontal asymptotes. Let's practice that with our next one. I'm going fast because I have 2 more examples and only 10 minutes. Okay, so vertical asymptote question. Well, that's going to happen when x plus 1 equals 0 because that's the denominator. So that is going to be when x equals negative 1. But this one is a different type. It has a log component, and the log component itself comes with a vertical asymptote. Remember what the log looks like? It comes with a vertical asymptote at 0. So I have, not y equals 0 goof. I am a goof. Vertical asymptote. So there's one by looking at it as a fraction, where is the denominator equal to 0? And there's one because of the presence of the log component. Okay, so I have two of them. Let's write it over here, x equal to 0, x equal to -1. I don't know what that graph looks like. Who knows? This is just a small piece to the puzzle. I'm not supposed to know. All I'm doing now is identifying where the vertical asymptotes sit. I have very little hope of quickly figuring out which arrows I get like I did for the rational function. Even if I can figure out these arrows, it's going to be wasted effort. Trust me, when I do step 3, it's going to be immediately obvious. I just have to wait. That's unfortunately how it is. The horizontal asymptote question, I now saw that in the case of the exponential function component, the answer to these limits are not the same necessarily. So I have to do them separately. I'll do the next one over here. Of course, the log and the exponential function are related, and it's reasonable to expect that I don't have symmetry. I lost my symmetry with their presence. One at a time, the top one. What is the form of this limit? See now why we emphasize the form so much? Because now it is super helpful. I don't even know how to do it without the form. L'Hopital's rule needs me to check the form first. Very important. Okay. X goes to positive infinity. What happens to the numerator? I read it off my graph. This is the graph of the natural log function. When x gets really big, it gets really big. Infinity. What happens to x plus 1? When x gets really big, it also gets really big. I have verified that I get one of the two forms needed in L'Hopital's rule, so I can use L'Hopital's rule. Because other than that, without some extra experience that I don't have at this stage, I don't know what the answer is here. I don't know. We're going to have to find out. So it is the same limit, but of the derivative of the top over the derivative of the bottom. Simplify that, and I get 1 over x, which is 0. Perhaps you're sitting there thinking, of course it was 0. No, I'm sorry, it is not obvious. It's not obvious. Especially as these things change. If I put a square there, what then? Is it still obvious? I don't know anymore. I need a fallback method because I don't have a good sense of how these two things can interact. It turns out that they interact in such a way the bottom one, even though it's linear, outgrows the top. Oops. Forcing everything to shrink down to 0. That wasn't obvious because I don't have a good sense for the natural log function yet. So that means I have a horizontal asymptote y equals 0 on the right. On the left, who knows what's going to happen? Check the form. X goes to negative infinity. What is the form of this? What happens to the natural log when x goes to negative infinity? That is a question I'm asking you right now. In order for me to see, do I use L'Hopital's rule? What's happening? I need to know how do the pieces behave when x goes to negative infinity. Well, certainly the bottom one is going to be negative infinity, right? It's just an x. The 1 does nothing. What happens to the log of x for x really big but negative? I'm asking so that you can assess your reaction. What do to figure it out? You have to do something, right? What I do, I look at my basic graph, read it off. What is happening to this graph far to the left? It's easier when I see the graph, right? So you have to be able to visualize this graph instantly so you can read off that information. For this graph, there is no far left. There is nothing here. It doesn't make sense. There is no function. It is undefined. It doesn't exist. It makes no sense because there is a piece in my function which is not defined. It's undefined. It makes no sense. If I'm asking for the limit, I'm asking for the behavior of the graph, which means there needs to be a graph, which means there needs to be a y value. There are no y values for some of these pieces, meaning there are no y values for the whole thing. This is undefined for x less than or equal to 0, meaning that nothing, no question involving those x values make any sense and should not be asked because of the presence of this log. It screws up the whole left side of a graph. It doesn't exist, which means I can't ask a question about something that doesn't exist. Okay, so what does this guy look like? I don't know, and I am not expecting myself to know. I know there is a couple of vertical asymptotes, 0 and -1. This one doesn't even make sense, right? -1. Because I'm never going to have a chance to even get there. So that guy's out too. And it's okay at this stage to think separately. And then when I want to graph the whole thing, I realize, oh, this -1 actually meant nothing. There is no graph there. So that wasn't crucial information. But it did, if there ever could have been those x values to consider, I should exclude -1. But because of the log, I can't even do that. So I don't have to list it, but if you did list it, totally fine. I don't mind. So this one actually looks very similar. It has a vertical asymptote here. It crosses. It does something very, whoopsie, very similar to the previous function, but it's not the same. The points where it turns and stuff, it's not the same. I have a vertical asymptote here. I have a horizontal asymptote on the right. Again, just from this step, there is no way for me to figure out this graph. It's not expected. But I want to at least give you an image that it can happen that I have a vertical asymptote here and a horizontal asymptote on the right and absolutely nothing on the left. It's a different kind of function, which is why it's categorized as a different type, because what happens when I try and graph it and analyze it is different from everything else. Okay. Oopsie. That's what I want to do. Lots of information. Lots of information. Just from listening to this lecture once may not be enough, and that's okay. I've tried to squeeze it in as much as I can. I still only have a minute left. Now for this guy, it's actually not bad. Step 2 is actually quite straightforward because we actually have a lot of properties similar to polynomials when it comes to step 2. This is not a polynomial, but I get a little bonus. With the complexity of this guy, and it's going to be a little messy later on, actually step 2 is kind of nice. My vertical asymptote question, I look at the denominator. Where is the denominator equal to 0? It's going to be at 0. So that's not bad. It's not bad. Right? Because I can't divide by 0 and there's nothing at the top to cancel it. It's going to blow up. So why is this 0 on its own? Vertical asymptote is the equation of a line, and the line is x equal to 0. Good. Horizontal asymptote question, I'm going to squeeze it in because it's actually quite straightforward. It is going to be approached the same way, ooh, wobbly x, the same way as a polynomial is. I get a little bonus here. This is not a polynomial, but because it is just powers of x added and subtracted, I can follow the same rule. This is going to behave like its leading term. What is the leading term? It is the highest power of x. So this is going to be the same as, I'm trying to finish, we're almost there, the highest power of x, or the most positive, the furthest on the number line to the right, however you want to say it. Now, perhaps I don't have a good sense of fraction powers of x, right? I personally actually don't. Rewrite it to a root, and it's much, much easier. Because I have a sense of a square root, and these are very similar. Work inside out. X is really large positive, so x squared is really large positive. Cube root of a large number that gets larger is going to be large. Okay. So I get a little bonus in that for how difficult these functions are eventually going to be, step 2 is not difficult. I do have to check what happens when x goes to negative infinity of my function in its polynomial looking form. It's not a polynomial, but luckily, when I look at long-term behavior limits, infinite limits, it follows the same strategy that the limit is going to behave, the function is going to behave the same as its leading term, which is the highest or most positive power of x. Now, perhaps I don't love the look of it. I prefer some roots. It just feels more intuitive to me. X is large but negative. X squared is going to make that large positive. Cube root of a large positive number, large positive. So, conclusion, no horizontal asymptotes. But I do know, ooh, I get two infinities. Almost done. I'm going to go up on either side. What happens in the middle? Oh, who knows? Seems to have a vertical asymptote as well. I don't know which one it's going to be. I get more information slowly, but it's a slow process. I need all the steps to really know the graph. But I have done something more. I do have more information that I didn't have previously. All right, so we have an example for each of our types of functions. For step 2, it's up to you how much you need to focus on which type, what you need to do. I understand we've gone really fast, perhaps, just trying to get everything in, because this is essentially the whole next portion for the midterm and so on. So there's a lot of things that are going to happen. Each of these steps is really its own topic to a degree. So we're going to loop back to step 2. Once we've individually looked at each step, we will go back and then take functions of each type and do the whole thing from step 1 to step 5 and see how the pieces come together. So you'll see step 2 again, but just try and get on top of the basic things that I see, basic approaches for the different kinds of functions, and let me know if you have any questions. Are there any questions right now you would like to ask? All right, the luxury of having a recording, watch the video over and over and over until you understand everything that I said, because everything is important and will make it easier as we move on. We will continue our discussion with step 3 tomorrow. Until then.